Australia is a big country. Australia is also a land shaped by wildfire in many places. Join me as we travel around this great country, meeting people and talking with them, and together their stories will come together and help us better explain Australia's complex relationships with wildfire. Welcome to Talking Wildfire Australia, my friends. Hi and welcome. This is Phil Cheney. He's a fire scientist from Australia. And today we're going to talk about large fire growth and different weather patterns that are prevalent in Australia. Phil, can you give us a talk?
Yeah, sure. I'll start off on Australia very broadly is a continent where at some stage in the development of vegetation over a season or a number of seasons, although we've got large areas that are qualified as desert, there can be times when those areas receive rain, and this year has been one of them. There's been lots of rain through the interior. There will be later large fires through all of that area. It's
Why is that, Phil?
well, it's semi-desert country. There's basically nothing to stop them. They'll be ignited by lightning, more than likely, but also human lighting is bound to occur, accidental fires.
And that's because of the fuel buildups that are happening because of the rain?
The rain has come down. We've got these ephemeral grasses that have all grown like mad. They've covered over what was formerly sandy desert, and now you have a continuous fuel. And we've had that build up over the last couple of years of very heavy rains which have extended right across Australia, including Central Australia. And we've had floods that have come down the Central Australian rivers into Lake Eyre. And so the result will be over probably next winter, when these grasses cure out, there will be potential leading into the fire season for northern Australia that these fires will develop and they'll burn huge areas because really there is no way of physically controlling them because there are very few natural barriers.
In the 1974-75 fire season, more than 117 million hectares were burnt. That's more than 15% of the total land area of Australia, and most of this was in Central Australia.
Now there are very different climates across Australia. If we start in northern Australia, in the Northern Territory, that's a monsoon tropical environment. The dry season extends from probably around late March, early March, April, through to about September. It's a dry season up there. The predominant wind direction is from the southeast to east, and it's often very consistent, and that was one of the reasons that I went up there to do a lot of grass fire experiments. We had consistent winds and consistent days. The fire danger never gets very high because the winds there don't reach high wind speeds. Then you go into the wet season where just before it's very humid, lots of lightning strikes, but much of the country has already been burnt by that stage. You shift over to Queensland, and Harry Luke, who was a forester in New South Wales, worked with MacArthur and they wrote the book Bushfires in Australia. Harry Luke described the march of the fire season, where the fire season in Queensland was July through to September. That's the dry season there. The winds there are westerly, often replaced in the afternoon by a sea breeze pushing in off the ocean. But the predominant wind, the dangerous wind, was a westerly. Again, rarely gets up to extreme strengths. As you come further south, then the peak season shifts around the Sydney area. It's really October through December, the end of December. By the end of December, there's usually some rain that comes in, and often that's the end of the fire season. Sometimes it'll predict longer, as it did in 2019. The fire season persisted through into January, but that is really a bit rare. You move around a bit further to Victoria, which has the worst fire climate, if not the world, certainly in Australia. It's equivalent to Southern California in America. The situation that creates this is a stationary high pressure system out in the Pacific, and that system circulates air in over Central Australia. It tends to stay there for a while, so this process can build up, and then moving across the south is the next cold front which is moving through. And as the cold front moves in, the isobars, the pressure lines, contract together and the wind speed gets stronger. And so in Victoria you can get wind speeds on a bad day. The winds are northerly to northwesterly in direction. Wind speeds might be up to 80 kilometres an hour, mean wind speed, 10 metres. And then as the cold front moves through, then the wind changes suddenly to a southwesterly wind, and this happens in a period of maybe 15 to 30 minutes. Sometimes there's a lull, and sometimes it comes with very little warning, unless you're tracking it. In Victoria, they often track the movement of this front towards where the fire is. You go across, if you go down to Tasmania, under these conditions, Tasmania is having a mild season because the low pressures are down. The bad season in Tasmania is when all the whole high pressure and low pressure systems travelling around the globe are moving further south. And so the winds that are coming in over New South Wales are moisture laden, they're easterlies, and you don't get a bad season in New South Wales, but they dry out as they go over Victoria, come down across Bass Strait into Tasmania, and then they get their occasional, maybe once every 15 years or so, a really bad season there. Strong northerly winds, again with that frontal system moving across the Great Australian Bight and hitting Tasmania and causing this sudden wind change. South Australia is a bit like Victoria, although it's somewhat less intense. Central Victoria has, again, the worst fire climate of Australia. If you were to rate them, you'd probably say Victoria 100, New South Wales ACT 60 or 70, Queensland 50, Western Australia 50 or 60, Northern Territory about 10. And it's all to do with this combination of pressure systems, wind speed, moisture content. The three things that are affecting how a fire burns. Western Australia, the dangerous wind is from the northwest. For most of most of the fire season in Western Australia is relatively benign. They have often have very stable spring periods where they can do prescribed burning, and the frontal changes that come into the coast of Western Australia often break down without forming a very strong frontal passage across the state. But every now and again it comes in, and this wind comes round and comes down from the northwest. It's dry from being up in the Kimberley region, a bit further south, Great Gibson Desert. Goes a little over the ocean but doesn't pick up any moisture and comes down as a dry northwesterly wind. And again you've got this frontal system which will cause somewhat of a change to the southeast and then eventually to the east, which is the stable summer wind. So within Australia we have all these patterns. The only place that doesn't burn is the rainforest of North Queensland. And that used to burn when the Aborigines went through it because they were so intense in their fire lighting that they created patches of eucalypt woodland in their pathways through the rainforest. But now you'll find an old open-grown woodland tree, a bit like you've got behind us here. I don't know if you can see it, but now there's rainforest trees shooting up all through. No way in the world it'll burn. So that's sort of a very broad description of the fire weather in Australia.
Phil, can you tell us a bit about how fires burn?
It's a big subject, Mike.
I agree.
Let's start saying combustion is a chaotic reaction. When a hydrocarbon breaks down, it eventually ends up as carbon dioxide and water and a host of almost any hydrocarbon you want to name in the world can be created in the process as a trace element or a trace compound in it. But that is a chaotic reaction. The process of a fire burning is a turbulent reaction. That means that flows are difficult to predict because they're mixing up. If you look closely at an individual flame, you'll see, let's say, coming out of a gas burner. Here's the gas coming out, and it burns as a diffusion flame, which means that the combustion is a narrow band where the gas meets the oxygen in the air. And that reaction happens in something that is a few micromillimeters in dimension. Now, the process of the heat released by that reaction creates turbulence. And so what that does is that turns the whole flames over, and with it the gas, and with it the air that is being entrained into the gas to create a flame which is a combination of unburnt gas,
Air,
a reaction boundary, and gas products coming out, mostly carbon dioxide and water. And the more intense the flame becomes, the more turbulent this is. Now, when a flame is in its initial single form, the radiation coming out of it is very low. But as it mixes in this turbulent flow, the different mixes of gas in that turbulent environment reinforces the radiation coming from it, so that the flame changes from almost a light bluey yellow colour to something which is bright red. And there are plenty of pictures that you can use for this to illustrate it. In the field, where we go when a fire is burning in natural fuels. It's the same process, and it's driven from, unlike a gas burner which is stationary, this fire is moving, and it gets its fuel by moving forward into new fuel. And so the process is then a reaction by what is pushing it forward, which is the prevailing wind near the fire, and the convection that the fire causes, which then interacts with the atmosphere above it. Now, if I can put it this way, when there is no wind, absolutely a fire starting at a point will spread out in a circular form. And the only irregularity to that circle is where the fuel is in patches. As the wind pushes it forward, the circle changes towards a parabolic shape at the front. And the wind is pushing it from behind, and if you want to describe the perimeter of the whole fire, an ellipse is a pretty good approximation. It's actually something a little different, but an ellipse is a pretty good approximation of the fire perimeter. Now, within that fire perimeter, because it's being pushed forward by the wind, the convection is focused above the front of the fire. And so the wind coming in and driving it forward comes in over the back of the fire, over the burnt ground, and down into the flames at the base of the leading edge of the fire, and then is drawn upwards in the convection column. This convection column, as the fire gets bigger and bigger, provides more and more interaction with the atmosphere and the wind field around it. Now, by and large, on any summer day, the atmosphere also is fairly turbulent, which means the wind is not only blowing horizontally, but it's also has rotation in it, which means that the direction of the wind in any particular position varies a lot. In forecasting wind speed for fire prediction, we would always take an average wind speed over something like 20 minutes to accommodate for this variation, which is in part absorbed by the fire and reflected by the process that the fire is spreading forward. The strength of the convection of the fire depends not only on how much fuel it is burning, but also what the structure of the atmosphere is. Now, as heat rises, whether it's in a fire or whether it's in a hot piece of ground that has been heated up by the sun, and it heats the air above it and it starts to rise, as it rises, it expands and it cools. And it cools at a rate which is called the adiabatic lapse rate. And this describes that if a fire rises 1,000 feet, and I can think of this better in feet because that's where I first learnt it. If the air rises 1,000 feet, then the temperature will drop by 3 degrees Celsius. The atmosphere usually has a structure which is less than that. The rate of temperature fall in altitude is at a rate as lower than the adiabatic lapse rate. So as a fire rises, it also cools, and it gets to a point where the gas in the convection column and the air that it's in train, of course it's always drawing air into it, gets to a point where in fact it's colder than the air outside, and so it starts to sink. And it eventually sorts out at a level, but often there is an inversion there, and the fire convection levels out at that level. When we move into really dangerous conditions, this temperature lapse rate of the temperature profile of the atmosphere is one where it's steeper than the adiabatic lapse rate or the adiabatic cooling rate. So as the convection column rises, it always, although it's cooling down, it always stays warmer than the air around it. And so it builds up to a level where you pass the condensation temperature, and of the fuel, the combustion of the fuel on the ground, a quarter of it ends up as water. The products are carbon dioxide and water and whole traces of other things, but basically carbon dioxide, 75% and 25% water. Now this water then starts to condense, and they're the white clouds that you see on the cumulus, on top of cumulus clouds in a sunny day without a fire, same process, and on top of a fire it reaches this level and this white cloud develops. There's as soon as the water starts to condensation, there's a change in the lapse rate, but it still rises, but it then cools at a different rate. But the same principle is that if it stays warmer than the outside air around it, it will continue to rise. And on the really big fires, the convection column may go over 40,000 feet. And so that's a product not only of the energy produced by the fire, but also the energy of the latent heat of condensation, because when the water in the convection column, the moisture changes from a gas to a water droplet, it releases heat. And that powers the further production, and finally it might go through, if the temperature structure is right, to a point where it's freezing. And so you get formation of icicle droplets. Now, these are all part of the complexity of a very large fire. Let's come back just for a minute to an ordinary fire. We have a fire, and it's a fairly bad fire, but it may not be this extreme situation. It's developed this parabolic front. It's got a strong convection column. The wind flow coming into the back of the fire is drawn into the base of the flames and then carried upwards. Wind is drawn in around the sides, but downstream there's a wake zone, as if the convection column was solid. And so the winds ahead of the fire are basically light and variable. For a triangle, which starts as the width of the head fire and may extend several kilometres downwind, and sort of until the winds coming around all of that reconvene and carry on. Now, I believe that this is a process that catches a lot of people by surprise. This whole business of suddenly there's a fire burning, you can see it coming, smoke, and when you're directly ahead of the fire, suddenly the wind stops. And people think, oh, wow, what a relief, the wind stopped. They don't realise that it's the fire that is blocking the wind getting to them. When embers fall out into this zone, they burn as little circles, because basically there's turbulent eddy winds there only, and these don't develop rapidly. And people said, oh, we'll go and put the spot fires out. And so they do. The next thing they know, and in Australia our condition is that most fires in the afternoon are driven by a westerly wind. So someone standing in front of the fire is looking at a fire which is blocking the sun, especially if it develops a huge convection column. And that can get very dark. In fact, it can almost go pitch black on a big fire as the fire front is approaching you. And the wind is light, you can't feel much. And then suddenly the whole fire catches up through. The person standing at the point where the fire front hits him is faced with not only the full strength of the wind, but also the acceleration of the wind caused by the combustion which has dragged the prevailing wind into the base of the fire and rocketed up in the convection column. They were standing in a dark environment where they were looking at this something coming toward them. Then they see the flames. Firstly, they see the fire reflected in the smoke above the fire. And this is a phenomenon which is very tricky. It can fool all sorts of people. It even fooled my boss, Alan MacArthur, who knew more about fires than anybody else at that time. But if you get in that situation, you see, oh, the red smoke is geez, the flames are high. No, hang on, take a hard look. There are the flames down there. They're the orangey red coloured things close to the ground. This is reflection of light off the smoke, and it's red. Now, during our fires in Canberra, people in a town directly downwind, under the smoke plume coming over them at Bungendore, were looking up, and they were looking into the smoke going across the top of them, and they saw red flashes. They said, wow, Canberra's in strife. Look at the red, there's flames in the convection column above us. What they were looking at was the sun coming through gaps in the cloud. Again, remember it's turbulent, so the whole thing's mixing up. And you got portions where the smoke was thin and the sun penetrated through and illuminated the black smoke and made it red, looked red. So here's a phenomenon which is very frightening, tricky to explain, tricky to make people believe you're right. I can add that too. But it happens. You've probably seen it yourself many times at night, where a fire at night is lighting up a whole lot of area around it. And when it's a big fire and it lights up the tops of the trees, it just illuminates them with this red glow. And if you're some distance away, you can say, wow, look at those flames. They're the full height of the forest. Where when you get up close to them, no, okay, they're pretty severe, but they're not the full height of the forest. It's, again, a reflected light. So this whole process of interaction of the fire consuming the fuel and burning up into the convection column is a basic process that allows us to look at actually how is a fire driven forward. Now, in recent years we've changed our opinion on this quite a bit. When we did our first experiments, we were looking at fires, ground fires, flame heights maybe 2 metres and not very big. We were measuring the wind behind the fire, under the forest canopy, and relating that to the wind speed above the canopy. Mm-hmm. And roughly speaking, it's about 3 to 1.
Okay.
Many cases. When we did our next series of big fires, in my Project Vesta, I had fires that were incipient crown fires in a tall eucalypt forest. They were high intensity fires, and with those we measured we tried to measure the wind in the forest. We couldn't do a very good job. We set up anemometers in the wind just behind it, and we had a couple of anemometers measuring out in the open to measure the outside wind. Now what was happening there is at the initial case, when the fire is burning forward, when it's only a litter fire, it doesn't change the field of the wind coming into the base of the fire. When you're burning through a fire with an understory, you have shrubs growing up, and this adds fuel, and it adds to the flame height, and it adds to the convection, but what it also does is it clears obstruction to the wind under the canopy. And so now, where the wind coming into the base of the fire is stronger than it was when the fire was small, simply because the obstruction of the shrubs had been removed. And if you go the next step further forward, where the flame heights are so great that it removes all of the canopy, then you have a situation where the only obstruction to the wind flow into the base of the fire is the trunks of dead trees. Well, not dead, burnt trees. No foliage on them, no canopy. And so now the wind force driving the fire, although it's the same wind that was the same as the original ground fire, now it's all coming down and can drive into the base of the fire, causing it to go even faster. Initially we did think that this was a stepwise procedure, resulted in more fuel being added to the fire, making it go faster. Now we understand that it's removal of that fuel. The fuel is necessary to be there, and to remove it you need to burn it. But it's the removal of the fuel that allows the wind in to blow the whole fire front forward. And I mean, I hope it's a relatively new concept in terms of how we look at predicting fire spread, and I hope that explanation helps you. But I think what's really important is understanding this complexity of interaction of convection caused by the fire, caused by the fuel it's burning, and the convection structure in the atmosphere, which can be very different from day to day. On some days it's very stable, convection columns don't rise. In other days it's unstable, and that's when we get the towering build-up of large fires. People say fires create their own wind, which is true to an extent, but it's not independent of the prevailing weather. And we tried fires where we tried to simulate a mass fire by burning huge amount of fuel, but if the weather was not unstable, we couldn't create. If the atmosphere wasn't unstable, we couldn't create a real conflagration fire.
Phil, what about the fires creating their own weather?
Well,
Like lightning or snow or...
Same process, isn't it? In terms of convective activity, a fire is somewhat different to a tornado, but not much. The tornado doesn't need extra energy put to it. It's all created by turbulence in the atmosphere and the latent heat of condensation of water. And the same thing in a thunderstorm downdraft. A fire will build up, thunderstorm will build up just from heating off the ground, an unstable condition. Same process, the air rises by itself, goes through the condensation layer, goes to great heights, gets cold, and then starts to sink and comes down. And when it rains, sometimes the rain hits the ground, sometimes it doesn't, but it blows out radially from the centre of the thunderstorm. A fire is only an addition to that. It usually happens when the atmosphere is dry, because that's what's created the situation for the fire. And yes, well, the same phenomena are happening. You've got it, the wind, the heat associated by the fire. It's not much different to heat associated off a concrete block or a black paddock out in the middle of nowhere. It heats up and it starts to rise. And if the atmosphere is unstable, the fire just provides that extra energy to carry it higher. Now, it goes through the same process. Water vapour, water condenses, can go into ice, gets cold, and then the whole lot sinks again and blows out. And same as in a thunderstorm, that process of dragging material upward causes static electricity, and you can create lightning out of it as well. So a fire is, in a way, only an additional action to a thunderstorm. Same processes. Is it creating its own weather? I don't know, I'd say it's creating weather phenomena, but I wouldn't say it's creating its own weather. That gives it some magical, some magical character that's difficult to understand. It's not much different to a thunderstorm, and most of the time it's less destructive in a local sense than a tornado is, which is purely atmospheric condensation and energy release, causing very violent winds.
Well, Phil, thanks for the chat today. It was really interesting. I learned a couple things out of that, and I'm sure everybody else has too. Thank you. We're doing this for all of you. If you like what we're doing, please give us a thumbs up, hit the subscribe button, and leave a comment below. See you next time.